Hello there, and welcome to Sleepy Science Vault. There's a place, a room designed to absorb nearly every sound wave that enters it, where people have walked in expecting peace, and walked out unsettled. Because in that room, they could hear themselves. Not their thoughts. Not their heartbeat in the poetic sense, but the actual, physical sound of their own nervous system firing. A low hum. A high-pitched tone. The quiet machinery of being alive. This is where the science of sound begins, not with noise, but with its absence. We tend to think of silence as nothing. A blank. The space between sounds. But silence, it turns out, is its own kind of presence. It has texture. It has weight. And in the right conditions, it can be almost overwhelming. Sound is measured in decibels, a scale of intensity that stretches from the faintest whisper of air molecules to the roar of a rocket engine. Most of us live somewhere in the comfortable middle of that scale, surrounded by the low hum of traffic, the murmur of ventilation systems, the ambient breath of a living world. But scientists can also use that same decibel scale to measure something far more elusive, the near total absence of sound. And what they've found is quietly astonishing. True silence, in any absolute sense, almost never occurs in nature. Even in the deepest forests at night, there is the rustle of wind and leaves, the distant call of an insect, the movement of air itself. The earth is always making sound. It has been making sound for 4.5 billion years, and it doesn't really know how to stop. So to find genuine quiet, you have to build it. Anechoic chambers are rooms engineered to absorb sound rather than reflect it. The walls are lined with long foam wedges, soft, geometric spikes that trap sound waves and prevent them from bouncing back. The floors are suspended. The doors are thick and sealed. Step inside one, and the silence doesn't arrive gradually. It lands on you all at once, like stepping into a different kind of atmosphere. And then, slowly, something unexpected begins to happen. In the absence of external noise, your auditory system doesn't go quiet. It becomes more sensitive. It reaches further into the silence, searching for something to process. And what it finds is you. The human ear, even in perfect stillness, is not passive. Your auditory nerve continues to fire spontaneously, small, random electrical signals that your brain interprets, faintly, as sound. In ordinary environments, these signals are completely masked by the world around you. But strip that world away, and they surface. A high tone. A low presence. A hiss at the edges of perception that you may have never noticed before. This is something most of us experience in milder form when we lie in a very quiet room at night. A faint ringing. A soft tone that seems to come from inside the head rather than outside it. It has been compared to tinnitus, the persistent internal sound that affects many people, but in these quiet moments, it isn't a condition. It's simply what your auditory system sounds like when nothing else is louder. In the 1950s, the American composer John Cage visited one of the world's first truly anechoic chambers, at Harvard University. He was a composer deeply interested in the nature of silence. He had even written a piece called 4 feet 33 inches, in which a performer sits at a piano and plays nothing at all, inviting the audience to listen to whatever sounds exist in the room around them. When Cage stepped into that anechoic chamber, he expected to finally hear silence in its purest form. Instead, he heard two distinct sounds. One high, one low. When he mentioned this to the engineer running the facility, he was told, matter-of-factly, that the high sound was his nervous system in operation, and the low sound was his blood in circulation. He was hearing himself. Cage left that room with a new understanding, that silence is not the absence of sound. It is the absence of intended sound. The world is always speaking, even when we ask it not to. Even when we build rooms designed to make it stop. Your ears, right now, are doing something remarkable. They are converting the faintest movements of air molecules into electrical signals that your brain translates into meaning. They are sensitive enough to detect vibrations smaller than the diameter of a hydrogen atom. And even in the deepest quiet they can find, they keep listening, generating their own soft signals, reaching into the stillness, never quite willing to let silence be truly complete. There is something quietly beautiful about that. The idea that your own body refuses to be silent. That even at rest, even in the dark, even in the most carefully constructed quiet in the world, you are still, softly, making sound. Everything you have ever heard began with something moving. A string pulled tight and released. A hand striking a surface. The rapid vibration of two vocal cords pressed gently together by a breath of air. Sound doesn't appear from nowhere, it is always the result of motion, of something disturbing the stillness around it and sending that disturbance outward into the world. At its most fundamental level, sound is a mechanical disturbance. When an object vibrates, it doesn't just move on its own, it pushes against the molecules around it. Those molecules press into the ones beside them, which press into the ones beside them, and on outward in every direction, a chain reaction of push and release spreading through whatever medium surrounds it. In air, in water, in wood, in bone, wherever there are molecules close enough to influence each other, sound can travel through them. This is what physicists mean when they describe sound as a mechanical wave. It doesn't carry matter from one place to another. The air molecules near a speaker don't travel across the room to reach your ear. Instead, they move back and forth in place, compressing together, then spreading apart, passing the energy of that movement along to their neighbors like a relay. What travels is not the molecule itself, but the disturbance, the pattern, the pressure. And the shape of that pattern is something called a longitudinal wave. Most of us grew up seeing sound illustrated as a smooth, curving line, peaks and valleys rolling gracefully across a page. And while that image captures something real about sound, the actual physical structure of a sound wave looks quite different. In a longitudinal wave, the movement of the molecules runs in the same direction as the wave itself is traveling. Think of it less like a ribbon waving in the wind, and more like a slow-moving crowd on a busy street, areas where people bunch together, followed by areas where they spread apart, moving forward in a single continuous flow. Those areas of bunching are called compressions. The places where molecules are pressed closer together than usual, where the pressure is momentarily higher. And between them are rarefactions, zones where the molecules have spread apart, where pressure drops briefly below normal. A sound wave, moving through the air around you, is essentially a repeating pattern of high pressure and low pressure, rolling outward from its source like the rings that spread across still water when a single drop falls into it. Which brings us to the shape of sound itself, because sound waves don't travel in lines. They expand in all directions at once, forming a sphere of pressure that grows larger and larger as it moves away from its source. If you could somehow see a sound, you would see it as an ever-expanding hollow globe, its surface rippling with waves of compression and release, spreading outward through the air the way light spreads outward from a flame, in every direction simultaneously, filling the space around it with the pattern of whatever created it. The intensity of that wave, how loud a sound is, depends on how much energy went into creating it. Loud sounds are born from large vibrations. When something strikes a surface with great force, or when a speaker cone moves through a wide arc, the compressions it creates are stronger, the pressure difference is more pronounced. Those waves carry more energy, and when they reach your eardrum, they push against it with greater force. A whisper barely moves the air. A thunderclap displaces it dramatically. The difference between those two experiences is simply a matter of how much the originating object moved, and how much energy it transferred into the surrounding medium. Pitch, on the other hand, is something different entirely. Where loudness is about the size of a wave, its amplitude, pitch is about its speed. More precisely, it's about frequency, how many of those pressure cycles pass a given point in 1 second. A high-pitched sound completes many cycles per second. A low-pitched sound completes fewer. This frequency is measured in units called Hertz, named after the German physicist Heinrich Hertz, and a healthy young human ear can detect sounds ranging from about 20 Hz at the low end, a deep, rumbling presence you almost feel more than hear, all the way up to around 20,000 Hz at the high end, a thin, sharp tone at the very edge of perception. Frequency and wavelength are intimately connected. Because sound travels at a fixed speed through a given medium, a wave that completes its cycle more quickly must have a shorter distance between each compression. Higher frequency means shorter wavelength. Lower frequency means longer wavelength. The deep resonance of a large bell and the bright ring of a small one are both traveling toward you at the same speed through the same air, but one is carrying long, slow waves, and the other is carrying short, rapid ones. All of this, the nature of vibration, the behavior of pressure waves, the relationship between frequency and pitch, the way sound expands through space, falls under the umbrella of a field called acoustics. The word comes from the Greek akoustichos, meaning relating to hearing, and the study of acoustics reaches into nearly every corner of human life. It shapes how concert halls are designed. It informs how microphones are built. It guides the way buildings are insulated, the way submarines detect objects underwater, the way doctors use ultrasound to see inside the body without ever making an incision. Acoustics is one of the oldest branches of science. The ancient Greeks were fascinated by the behavior of sound in their open-air theaters, some of which were designed with such precision that a performer standing at the center of the stage could be heard clearly by every one of the thousands of people seated in the rows above. Those designers may not have had the mathematical language to describe what they were doing, but they understood, intuitively, something true and enduring about the nature of sound. Sound is not mysterious. It follows rules. It behaves predictably. It can be measured, modeled, manipulated, and understood. And yet, knowing all of that, there is still something that feels almost magical about it. The fact that every sound you have ever heard, every piece of music that has ever moved you, every voice that has ever meant something to you, arrived as nothing more than a pattern of pressure. Molecules pressing against molecules. A mechanical disturbance, moving outward through the air, finding its way, eventually, to you. When lightning splits the sky, the light reaches your eyes almost instantly. The flash is there and then it's there, no delay you could meaningfully measure, no sense of it traveling toward you at all. It simply arrives. The sound is different. The thunder comes later. Sometimes a second later. Sometimes 5, or 10, or 20. And in that gap between the flash and the rumble, you can feel something that is surprisingly rare in everyday experience, the actual speed of sound, made visible by the speed of something faster. Sound travels at roughly 1,235 kilometers per hour through air at a comfortable room temperature of about 20 degrees Celsius. That is fast by almost any ordinary standard. Faster than any car, faster than most aircraft, faster than a rifle bullet. But light travels at nearly 1 billion kilometers per hour. The difference between them is so extreme that for almost any distance we encounter in daily life, light is effectively instantaneous, while sound takes its time. This is why we count the seconds between lightning and thunder. Every 3 seconds of delay corresponds to roughly 1 kilometer of distance. The storm is a clock, if you know how to read it. Thunder itself is a remarkable thing. What you're hearing is not the lightning directly, it's the air around it. A lightning bolt heats the air it passes through to temperatures of around 30,000 Kelvin, roughly 5 times hotter than the surface of the sun, and it does this in a fraction of a millisecond. The air has no time to expand gradually. It explodes outward faster than sound can travel through it, creating a shock wave, and that shock wave is the crack of thunder. The long, rolling rumble that follows is simply that initial explosion arriving from different points along the length of the bolt, which may stretch for several kilometers, each section reaching you a fraction of a second after the last. But here is something that surprises many people: the speed of sound is not a fixed constant. It changes depending on the medium it's traveling through, and even within the same medium, it changes depending on conditions. Temperature is one of the most significant factors. Sound travels through air by passing energy from one molecule to the next, and warmer air contains molecules that are moving faster and colliding more energetically. When the molecules are already vibrating rapidly from heat, they can pass along the compression of a sound wave more quickly. This means that sound travels faster on a warm summer afternoon than on a cold winter morning. The difference is meaningful. A change of just 10 degrees Celsius can alter the speed of sound in air by several meters per second. For engineers designing precision acoustic instruments, or for musicians performing outdoors in changing weather, this is not a trivial consideration. But temperature only tells part of the story. The medium itself matters far more than any temperature adjustment. And this is where the behavior of sound becomes genuinely fascinating. Sound travels through water at approximately 1,480 meters per second, roughly 4 times faster than through air. The reason for this comes down to density and elasticity. Water molecules are packed far more closely together than air molecules, which means a compression wave can be passed along much more efficiently. There is less distance between each molecule, less time wasted, less energy lost in the handoff. The wave moves with greater speed and, in many cases, with far less attenuation, meaning it can travel enormous distances without fading significantly. This property of underwater sound has shaped the behavior of ocean life in ways that are still being discovered. Whales, for instance, communicate across distances that would be impossible in air. The low-frequency songs of blue whales can propagate through ocean basins for hundreds, and in some cases thousands, of kilometers. There's even a natural acoustic layer in the deep ocean, a zone where temperature, pressure, and salinity combine to create a channel that traps and guides sound waves, allowing them to travel with extraordinary efficiency. This layer, known as the SOFAR channel, was discovered and used by the military during the 20th century, but the ocean's creatures had been using it for far longer. If water accelerates sound relative to air, then solid materials take that principle even further. The molecules in a solid are not just close together, they are locked into rigid structures, bound to one another by forces far stronger than the loose interactions between fluid molecules. When a compression wave enters a solid, it moves through that crystalline lattice with remarkable speed. Sound travels through steel at around 5,100 meters per second, more than 3 times faster than through water, and roughly 15 times faster than through air. This is not merely an abstract physical curiosity. It has a deeply practical dimension that becomes apparent every time the Earth itself moves. Earthquakes generate several types of seismic waves, and the fastest of these, the primary waves, or P waves, are essentially sound waves moving through solid rock. Because rock is a rigid solid, these waves travel at extraordinary speeds, sometimes exceeding 8,000 meters per second deep in the Earth's mantle. They are the first waves to arrive at seismograph stations after a quake, which is precisely why they are called primary waves. They arrive before anything else. The secondary waves, which move the ground in a different manner, travel more slowly. The surface waves, which cause most of the visible shaking and damage, are slower still. Seismologists use this difference in arrival times to triangulate the location of an earthquake's origin point, known as the epicenter. By comparing when the different wave types reach multiple stations across a region, they can calculate with considerable precision exactly where and how deep the rupture occurred. It is, in a sense, a form of listening, using the travel times of sound like waves moving through the solid earth to read a story written in rock. There is something quietly profound in all of this. Sound, which we think of as something light and transient, a conversation, a piece of music, a momentary disturbance in the air, is also the force that moves through mountains. It is present in the groan of shifting tectonic plates and in the low rumble that travels through the ground before a major quake arrives. It passes through the ocean floor and through the continental crust, through iron and granite and basalt, carrying information about the interior of a planet that no human has ever seen and no instrument has ever directly reached. We tend to experience sound as something intimate and immediate, something that happens in the space between one person and another, in a room, in a moment. But it is also something that operates at geological scale, moving through the deep structure of the world with patient, unhurried force. The same physical principle that carries a whisper across a quiet room also carries the memory of an earthquake across an entire continent. Sound can bend. Not in the dramatic, visible way that light bends through a prism, splitting into color, but in a quieter, more subtle way that most of us have noticed without ever thinking much about it. You can hear someone speaking in the next room even when the door is closed. You can hear music drifting around the corner of a building before you can see its source. Sound reaches you from directions you wouldn't expect, traveling around edges and through gaps, finding its way to you by routes that seem almost indirect. This behavior has a name: diffraction. When a sound wave encounters an obstacle or passes through an opening, it doesn't simply stop at the edge or cast a sharp acoustic shadow the way light casts a visual one. Instead, it spreads. The wave bends around the obstacle, reconstituting itself on the other side, continuing its journey in slightly altered form. How much bending occurs depends on the relationship between the size of the obstacle and the wavelength of the sound. Low-frequency sounds, with their long wavelengths, bend more readily around large objects, which is why the deep bass from a neighbor's music seems to pass through walls more easily than the higher frequencies do. This is one of the quieter miracles of everyday acoustic life. The world is full of surfaces and barriers and angles, and yet sound navigates all of them with a kind of fluid persistence, finding paths that rigid, straight-line travel would never allow. But there is one condition under which sound cannot travel at all. Not slowly, not differently, simply not at all. That condition is a vacuum. Sound is a mechanical wave. It requires a medium, molecules to compress, to pass energy between them, to carry the disturbance forward. Remove those molecules entirely, and there is nothing for the wave to move through. The vibration has nowhere to go. It dies at the source, instantly and completely. Outer space, in its vast expanses between planets and stars, is as close to a true vacuum as nature provides. The density of matter in interstellar space is almost incomprehensibly low, sometimes just a handful of atoms per cubic meter, compared to the roughly 10 to the power of 25 molecules packed into every cubic meter of the air around you right now. In those conditions, sound as we understand it simply cannot propagate. If the sun were to produce a sound, and in a sense it does, from the immense convective turbulence churning beneath its surface, that sound would never reach us. The 150 million kilometers of near vacuum between here and there would silence it completely before it traveled any meaningful distance. This is why space, for all its visual drama, is acoustically nothing. The collision of galaxies, the explosion of a star, the shock wave of a supernova expanding outward at millions of kilometers per hour, all of it happening in total, profound silence, at least from any distance. The universe is the largest anechoic chamber that exists, not because it absorbs sound, but because it has removed the very possibility of it. Communication across that silence requires something different. Radio waves, which are electromagnetic, not mechanical, can travel through a vacuum at the speed of light, carrying information without needing any medium at all. This is how mission control speaks to astronauts in orbit, how the Voyager probes send their data back from the edge of the solar system, how deep space telescopes relay their findings across hundreds of millions of kilometers. Not sound, but its electromagnetic cousin, a wave that needs nothing to travel through, that crosses the void as naturally as sound crosses a room. Astronauts preparing for spacewalks train in environments designed to approximate that silence. Anechoic chambers, the same kind of sound-absorbing rooms we encountered earlier, in the context of hearing your own nervous system, are used to prepare crews for the acoustic isolation of working in space. Outside the vehicle, in a suit, there is no ambient sound. No hum of machinery transmitted through air, no background murmur of a living environment. Communication happens entirely through radio, voice carried electronically from one suit to another, never touching the void between them. The silence outside is absolute and it does not relent. There is something strangely moving about that image, a human being, floating in silence so complete it has no parallel on Earth, speaking into a microphone so that another human being a few meters away can hear them. Two people separated by a medium that erases all sound, staying connected through a technology that bypasses the need for it entirely. And then, eventually, they return. The hatch closes. The atmosphere fills the cabin. And the world of sound comes back, the hum of systems, the rustle of movement, the ordinary acoustic texture of being inside a human-made space. After the silence of the void, even that modest sound must feel like a kind of homecoming. Which brings us back to where this all began, back to the ear. Back to the body. Back to the extraordinary biological instrument that makes any of this experience possible in the first place. The human ear is sensitive to a range of frequencies stretching from about 20 Hz at the lowest end to around 20,000 Hz at the highest. That range, 20 cycles per second to 20,000, spans a remarkable breadth of acoustic experience. At the low end sit the deep resonances of large structures, the rumble of distant thunder, the fundamental notes of a pipe organ, the bass frequencies that you feel as much as hear, vibrating in your chest and your feet and the surfaces around you. At the high end are the thin, bright frequencies of small, rapid vibrations, the upper harmonics of a violin, the faint ring of a crystal glass, the high call of certain birds at the edge of what human hearing can resolve. This range is not universal. Many animals hear far beyond it in one direction or another. Dogs can detect frequencies up to around 65,000 Hz. Cats, somewhat higher. Bats navigate by producing calls that reach 100,000 Hz or more, far above the ceiling of human perception. Elephants, at the other extreme, communicate through infrasound, frequencies below 20 Hz, too low for human ears to register, rumbles that carry across several kilometers of open savanna, carrying information about water, danger, and the location of other members of the herd. The human range sits in the middle of this broader acoustic spectrum, shaped by millions of years of evolution to be most sensitive to the frequencies that matter most in human life, and, above all, to the frequencies of the human voice. Inside your ear, the mechanism that converts all of those pressure waves into the experience of sound is breathtakingly delicate. After sound enters the ear canal and sets the eardrum in motion, after those vibrations are amplified by the 3 tiny bones of the middle ear, the smallest bones in the entire human body, the wave enters a fluid-filled spiral structure called the cochlea. And here, lining the interior of that spiral, is a structure called the basilar membrane, upon which sit some of the most specialized cells in the human body. They are called hair cells, and they are the final translators. Each one carries a tiny cluster of microscopic projections on its surface, hair-like structures that move in response to the fluid waves traveling through the cochlea. When those hairs are deflected, bent by the mechanical energy arriving from outside, the cell generates an electrical signal. That signal travels along the auditory nerve to the brain, where it is processed, interpreted, and transformed into what you actually experience as sound. The cochlea performs a remarkable feat of frequency analysis as it does this. Different regions of the basilar membrane respond most strongly to different frequencies. The base of the spiral responds to high frequencies, the apex to low ones. When a complex sound enters the ear, containing many frequencies simultaneously, the cochlea essentially separates them out, routing each frequency to the part of the membrane tuned to receive it, generating a spatial map of sound that the brain can then read and interpret. You have, at this moment, roughly 16,000 hair cells in each of your 2 cochleae. That is the entire population of cells responsible for your hearing, all of it. They cannot regenerate. Unlike most of the cells in your body, which are replaced over time, hair cells lost to damage or age or excessive noise exposure are gone permanently. They do not come back. This is one of the more sobering facts in the biology of hearing, and also one of the reasons why the quieter hours matter. Not just for rest, not just for sleep, but for the preservation of something genuinely irreplaceable. Those small, extraordinary cells have been with you since before you were born. By the time a fetus is around 20 weeks into development, the cochlea is already structurally complete. Hearing is one of the first senses to fully form, and one of the last to fade as life ends. It is, in the deepest sense, the sense that accompanies us longest. The eardrum is thinner than a sheet of paper. Not much thinner, just slightly, but the comparison is worth sitting with for a moment. That membrane, stretched across the end of your ear canal like the skin of a drum, is the first structure in your body to receive the pressure waves traveling toward you from the world. It is your primary interface with sound. And it is extraordinarily, almost improbably delicate. Its thinness is not a design flaw. It is precisely what makes it work. A thicker membrane would be stiffer, less responsive to the subtle pressure variations carried by quiet sounds. The eardrum's remarkable sensitivity comes directly from its fineness, its willingness to move in response to even the most gentle disturbance in the air. It is built to be moved, and it does its job with extraordinary precision. The hairs that line the inner ear, those irreplaceable hair cells we encountered in the last section, are among the finest biological structures in the human body. The stereocilia, the tiny projections that sit atop each hair cell and bend in response to fluid movement, are some of the thinnest filaments produced by any human tissue. They operate at a scale where the ordinary vocabulary of size starts to lose its meaning, deflecting by distances measured in nanometers, billionths of a meter, and yet generating, from those minute movements, the full range of what you experience as sound. There is a precision to all of this that becomes more remarkable the closer you look. When a sound wave reaches your ear, the entire process of reception and initial processing happens almost instantaneously. The human auditory system processes incoming sound in approximately 0.05 seconds, 50 milliseconds from the moment a pressure wave strikes the eardrum to the moment the brain registers it as sound. That is fast. Faster than a blink. Fast enough that sound feels, experientially, like something that simply is rather than something that arrives and is processed. But even that figure, impressive as it is, understates the resolution of the system. Your auditory system can distinguish between two sounds arriving as little as 10 microseconds apart, 10 millionths of a second. A gap so small it has no analog in ordinary experience, no everyday comparison that captures how fine that discrimination really is. And yet your brain uses exactly this ability, constantly and without effort, to do something that seems simple but is in fact a sophisticated spatial calculation. It figures out where sounds are coming from. You have two ears, and they are separated by the width of your head, roughly 15 to 20 centimeters, depending on the person. A sound arriving from your left side will reach your left ear a tiny fraction of a second before it reaches your right. It will also be slightly louder in the left ear, because the head itself acts as a mild acoustic barrier, absorbing a small amount of the sound's energy before it reaches the far side. These two differences, the interaural time difference and the interaural level difference, are the primary cues your brain uses to locate sounds in the horizontal plane. Each ear, then, is not simply a duplicate of the other. They serve different, complementary roles in building your spatial model of the acoustic environment. Your left ear is your primary receiver for sounds on the left. Your right ear is primary for sounds on the right. The brain is continuously comparing the signals from both, measuring the tiny differences in timing and intensity, and constructing from those measurements a sense of where in three-dimensional space each sound is located. The shape of the outer ear, the visible, folded structure called the pinna, contributes to this process as well. Its complex curves and ridges subtly alter the frequency content of sounds before they enter the ear canal, and they do so differently depending on whether the sound is coming from in front of you, behind you, above or below. The brain learns these spectral signatures over a lifetime of listening, and uses them to resolve ambiguities that timing and level differences alone cannot solve. Sounds arriving from directly in front and directly behind, for instance, might reach both ears at exactly the same time, but the pinna's filtering distinguishes between them. This is why recordings made with microphones placed inside ear canals, a technique called binaural recording, can produce an uncanny sense of three-dimensional space when listened to through headphones. The microphones capture not just the sound, but the acoustic shaping applied by the listener's own pinna, preserving the spatial cues that the brain is built to decode. Listen to a well-made binaural recording in the dark, and sounds seem to move around you, to come from above and below, from behind and beside, a fully inhabited acoustic space conjured from nothing but air pressure and two small speakers pressed against your ears. What is less commonly known is that your ears don't stop being useful when the conversation turns from hearing to something else entirely. They also keep you upright. Deep inside the inner ear, nestled alongside the cochlea in the same bony labyrinth, are the vestibular organs, a set of fluid-filled chambers and canals responsible for your sense of balance and spatial orientation. There are 3 semicircular canals, each oriented in a different plane, and 2 smaller structures called the utricle and saccule. Together, they detect rotational movement, linear acceleration, and the direction of gravity. They tell your brain which way is up, how fast you are turning, and whether you are accelerating or decelerating. This system is why you can walk in the dark without falling. It is why you can close your eyes and still know whether you are tilting. It is why, when you spin in place and then stop, the world seems to continue rotating. The fluid in the semicircular canals keeps moving briefly after your body has stopped, sending signals to the brain that conflict with what your eyes now report, producing the familiar, momentarily disorienting sensation of dizziness. The ear, then, is not only a sound detector. It is a full-body orientation system, an instrument of balance as much as hearing, a sense organ whose influence extends far beyond the simple reception of acoustic information. And protecting all of this, the delicate drum, the fluid-filled canals, the irreplaceable hair cells, is a set of mechanisms that the body has developed over a very long evolutionary history. Earwax, which tends to be regarded with mild distaste, is in fact a remarkably well-designed protective substance. Produced by glands in the outer ear canal, it serves several functions simultaneously. It traps dust, debris, and microorganisms before they can reach the more delicate inner structures. It has mild antibacterial and antifungal properties. And it moves slowly outward from the ear canal of its own accord, carried by the natural migration of skin cells and assisted by the movement of the jaw, which is why chewing and talking are, in a very minor way, part of the ear's self-cleaning process. The body has, in other words, engineered a conveyor belt for removing contaminants from one of its most sensitive organs, and it runs continuously and without any conscious instruction. Further inside, there is another layer of protection. The middle ear contains 2 small muscles, the tensor tympani, attached to the malleus, and the stapedius, the smallest skeletal muscle in the human body, attached to the stapes. Together, these muscles form what is called the acoustic reflex. When the brain detects an incoming sound that is dangerously loud, it triggers these muscles to contract, stiffening the ossicular chain and reducing the amount of energy transmitted to the inner ear. The whole process takes about 25 milliseconds, fast enough to provide meaningful protection against many kinds of sustained loud noise, though not fast enough to protect against sudden, instantaneous sounds like an explosion, which deliver their damage before the reflex has time to engage. Interestingly, the acoustic reflex also activates just before you speak. The brain sends a signal to those middle ear muscles a fraction of a second before your vocal cords begin to vibrate, preemptively reducing the sensitivity of your own hearing to your own voice. This is part of why your voice sounds so different to you on a recording than it does in your own head. You are always hearing yourself with a slight damping applied, while others hear you without it. the ear is not a passive receiver. It is an active, adaptive, self-protecting system, one that has been refined over hundreds of millions of years of evolution, from the pressure-sensitive cells of ancient aquatic creatures to the sophisticated bilateral instrument that now lets you locate a whisper in a dark room, stay balanced on a moving surface, and hear, in a few tens of milliseconds, the full acoustic texture of the world around you. All of it housed in a space smaller than your thumbnail. All of it working, quietly and continuously, for as long as you are alive. By the time a sound reaches your brain, the hard part is already over. The eardrum has moved. The ossicles have amplified. The cochlea has separated the frequencies and converted them into electrical signals. The auditory nerve has carried those signals inward. All of that mechanical and biological work, the translation of pressure into electricity, has already happened before the brain processes a single moment of what you are about to hear. And yet, in another sense, the hard part is only just beginning. Because what the brain does with sound is not simply reception. It is not a passive recording of what arrived. It is something far more active, far more constructive, and in some ways far stranger than the physics of the ear would suggest. The brain processes sound and rhythmic patterns of electrical activity, waves of neural firing that pulse through the auditory cortex in cycles. These oscillations are not incidental background noise in the brain's processing. They appear to be fundamental to how sound is organized and interpreted. The brain seems to entrain itself to the rhythms of incoming sound, synchronizing its own oscillatory activity to the patterns it is receiving, using those rhythms as a kind of temporal scaffold on which to hang the details of what it is hearing. This happens at multiple timescales simultaneously. There are fast oscillations tracking the fine acoustic structure of individual sounds, and slower oscillations tracking the broader rhythm of speech or music. The brain is, in a real sense, dancing with the sound it receives, not merely recording it, but actively moving in time with it. One of the more striking details in the neuroscience of sound perception involves a number, 1/6 of a second. Roughly 160 to 170 milliseconds. This appears to be a fundamental unit of human perceptual and decision-making time, a window within which the brain integrates incoming information before committing to an interpretation. It appears in reaction time research, in the study of conscious awareness, and in the way the auditory system groups rapid events into coherent perceptual units. The brain, it seems, does not process the world as a continuous stream but as a series of discrete snapshots, each roughly 1/6 of a second wide, stitched together into what feels like seamless experience. Sit with that for a moment. What feels like the continuous flow of hearing, the smooth, uninterrupted experience of listening to a voice or a piece of music, is, at the neural level, a sequence of discrete processing windows. Frames, in a sense. The brain constructs the impression of continuity from what is actually a rhythmic, flickering process. This connects to something researchers call event segmentation. The world, acoustically speaking, is a continuous stream of pressure variations. There are no clear boundaries in the physical signal between one sound event and the next, no gaps, no labels, no natural punctuation. And yet we don't experience the acoustic world as an undifferentiated flow. we hear things. A word. A footstep. A door closing. A bird call. Separate, distinct events, each with a beginning and an end. The brain creates these boundaries. It actively segments the continuous stream of incoming sound into discrete events, using statistical regularities in the signal, changes in frequency, in intensity, in rhythm, to decide where one event ends and another begins. This segmentation happens automatically, below the level of conscious awareness, and it is happening right now as you listen to these words, carving the continuous sound of a voice into individual words, phrases, and meaningful units. What is genuinely surprising, and what challenges a simpler, older model of how perception works, is what the brain does with silence. For a long time, the intuitive assumption was that silence was simply the absence of input. When no sound arrives, the auditory system rests. Processing pauses. The brain waits for the next signal. Silence, in this view, was a neutral state, the baseline from which sound perception departed and to which it returned. This turns out to be wrong. Research in the last decade or so has shown that the brain processes silence actively, in much the same way it processes sound. When a sound stops, the auditory system doesn't simply switch off. It continues generating predictions about what should come next. It monitors the silence, measures its duration, compares it against expectations built from what came before. Silence, neurologically, is not a pause in perception. It is a continuation of it. This means that what you experience when you sit in a quiet room is not the absence of auditory experience. It is a genuine perceptual state, one that the brain is actively constructing and maintaining. Silence, in the brain's processing, is as real as sound. It has content. It has duration. It has meaning. The brain attends to it, tracks it, and draws information from it, information about endings, about transitions, about the structure of the auditory environment. There is something almost philosophical in this finding. We tend to think of silence as nothing, as the default state from which sound departs. But the neuroscience suggests that silence is not nothing. It is something the brain makes, out of the absence of acoustic input, through the same active, constructive process it uses to make everything else it perceives. Perception, in general, is not passive. This is one of the most important and counterintuitive findings of modern neuroscience. We do not simply receive the world through our senses and experience it as it is. We construct our experience, actively, continuously, using a combination of incoming sensory data and top-down predictions generated by the brain based on prior experience, context, and expectation. The brain is, in a very real sense, a prediction machine. It is constantly generating a model of what the world is likely to be doing, and comparing that model against the actual incoming data. When the data matches the prediction, processing is efficient and experience feels smooth. When the data violates the prediction, the brain updates its model, generating what we experience as surprise, or novelty, or the sudden sharpening of attention. This predictive architecture shapes everything you hear. When you listen to speech in a noisy environment, your brain is not simply trying to detect the acoustic signal through the noise, it is using its model of language, of the speaker's voice, of the likely content of the conversation, to fill in gaps and resolve ambiguities that the raw acoustic data alone could never resolve. When you listen to familiar music, your brain is anticipating what comes next, and the pleasure of that anticipation, and of its occasional, carefully timed violation, is a significant part of what makes music emotionally powerful. For about 30 years, the dominant model of sound adaptation held that when the same sound was presented repeatedly, the auditory system simply habituated to it, neurons became less responsive, the signal was progressively dampened, the brain tuned it out. A simple, mechanical fatigue. A dimmer switch being gradually turned down. Recent research has revealed this picture to be considerably more complex. What appears to be happening is not simple fatigue but active prediction, the brain learning the statistical regularities of a repeated sound and building an increasingly precise model of it, then suppressing its own response not because it is tired, but because the sound has become expected. The neural response is being actively cancelled by prediction, not passively extinguished by repetition. The practical implication of this is something many of us have experienced. A clock ticking in a quiet room seems loud at first, then fades from consciousness as the brain learns to predict and suppress it, then seems to return to awareness the moment it stops, because the brain was expecting a tick that did not arrive, and that violated prediction snaps attention back. You don't notice the sound while it is happening. You notice it when it stops. The brain, then, is not a recorder. It is a modeler, continuously building, testing, and revising its account of the acoustic world, using silence as actively as sound, using prediction as actively as perception, constructing moment by moment the experience of hearing from a combination of what is actually there and what it confidently expects to find. And sometimes, in ways that are genuinely delightful, that constructive process produces things that are not there at all. If you have ever listened to a phone call with poor reception, or heard a voice through a wall, or tried to follow a conversation in a very noisy room, you have likely had the experience of understanding words that, if you analyze the raw acoustic signal, were never actually delivered clearly to your ears. The brain filled them in. It used the context of the sentence, the rhythm of the speech, the identity of the speaker, and its vast accumulated knowledge of language to reconstruct words from fragments, to hear, clearly and confidently, things that the acoustic signal alone could not have supported. This is not a glitch. It is a feature. The brain's ability to restore missing or degraded acoustic information, a phenomenon researchers call auditory restoration, or the phonemic restoration effect, is one of the most elegant demonstrations of just how active and constructive auditory perception really is. Present a listener with a recording in which a phoneme has been replaced by a burst of noise, and in most cases they will not hear the noise at all. They will hear the complete, intact word, with all its sounds present, even though one of those sounds was never actually there. The brain invented it. Not randomly, but correctly, because it had enough context to know what should have been there, and it simply provided it. You are not hearing the world. You are hearing the brain's best, continuously updated, remarkably accurate theory of the world. Most of the time, that theory is so good, and so seamlessly maintained, that the difference between the theory and reality never becomes apparent. It is only at the edges, in illusions, in noise, in silence, in the quiet moments when the expected sound fails to arrive, that you catch a glimpse of just how much work is being done, invisibly and constantly, to give you the experience of simply listening. Context changes everything you hear. Not in a vague, impressionistic sense, but in a precise, measurable, neurological one. The same acoustic signal, arriving at your ears with identical physical properties, can be perceived as two entirely different things depending on what came before it, what surrounds it, or simply what the brain has been primed to expect. The sound itself hasn't changed. Your experience of it has, completely. This is one of the deeper implications of what we explored in the last section, that perception is construction. If the brain is building its experience of sound rather than simply receiving it, then the materials it builds with, context, expectation, prior experience, matter enormously. Change those materials, and you change the building, even if the raw sensory input stays the same. Auditory illusions are the clearest demonstrations of this principle. They are not tricks in the dismissive sense, not mere curiosities that reveal the brain to be occasionally foolish. They are windows. Each one shows something true and specific about how the auditory system works, what assumptions it makes, and what happens when those assumptions are deliberately exploited. One of the most elegant examples involves melody and the perception of musical streams. When a sequence of notes is played in a certain way, alternating rapidly between two registers, high and low, the brain doesn't always hear it as a single continuous melody. Instead, it can split the sequence into two separate melodic lines, one high and one low, each running in parallel, as though two instruments were playing simultaneously rather than one. The composer wrote a single part. The listener hears two. This phenomenon is called auditory stream segregation, and it is not an error. It reflects the brain's fundamental organizational tendency to group sounds that share similar properties and separate sounds that differ significantly. In a natural acoustic environment, sounds that are close in pitch and timbre tend to come from the same source, while sounds that differ markedly tend to come from different sources. The brain applies this heuristic automatically, and when a musical passage is constructed in a way that trips that heuristic, the listener experiences the musical world reorganizing itself, streams splitting and merging in ways the composer may never have intended. Baroque keyboard music is particularly rich in this effect. Composers like Bach wrote single melodic lines that, when played at tempo, naturally segregate into two or more implied voices, an illusion of counterpoint created from a single strand of notes. Whether Bach was consciously exploiting auditory stream segregation or simply discovered it intuitively through musical practice is a question that may not have a clear answer. But the effect is real, reproducible, and grounded in the same neural architecture that helps you follow one conversation in a room full of voices. Then there are the illusions that involve rhythm and time, and these are, in some ways, the most disorienting of all, because they target something we tend to trust implicitly, our sense of how fast things are moving. The shepherd tone is perhaps the most famous acoustic illusion involving pitch. Named after the cognitive scientist Roger Shepard, it is a sound that appears to rise continuously in pitch, and yet never actually gets higher. It achieves this through a carefully constructed layering of tones across multiple octaves, with the higher tones fading out as they ascend and new lower tones fading in to replace them, so that the overall impression is of perpetual ascent with no arrival point. The auditory equivalent of an Escher staircase, climbing forever without reaching a higher floor. The rhythmic analog of this, the Risset rhythm, developed by composer Jean-Claude Risset, applies the same principle to tempo. A rhythmic pattern can be constructed that seems to accelerate continuously, its pace always increasing, and yet after any given interval returns to roughly where it started, the acceleration having circled back on itself without the listener noticing. The sensation of speeding up is genuine and persistent. The reality is a loop. What both of these illusions reveal is something important. The brain's perception of pitch and tempo is not an absolute measurement. It is a relative judgment, made by comparing the current state to recent history. The auditory system is exquisitely sensitive to change, to things moving up or down, faster or slower, but it is much less reliable at tracking absolute position. It notices direction of movement more reliably than destination. And so, when an illusion is constructed that always appears to be moving in one direction without ever arriving anywhere, the brain keeps updating its sense of position and keeps finding motion, indefinitely. What makes the next step in this story particularly striking is where researchers decided to take these findings, because they took them somewhere that initially seems to make no sense at all. They tested whether auditory illusions work with silence. Not with sounds that create illusions. With the gaps between sounds. With the absences. And what they found was that silence produces the same illusions as sound. Present a listener with a Shepard tone-like pattern constructed from silences rather than tones, a series of carefully timed gaps whose structure mirrors the ascending layering of the original illusion, and the perception of endless ascent persists. The brain, encountering the structured absence of sound in the same pattern it has learned to associate with rising pitch, produces the sensation of rising pitch. From nothing. The same result holds for temporal illusions. Structured silences can generate the same continuous acceleration effect as the Risset rhythm. The same distortions. The same looping sensation of endless change without progression. This finding carries a weight that goes beyond the neat demonstration of a perceptual effect. It means that what the brain is doing when it processes sound is not, at the deepest level, really about sound at all. It is about pattern. About structure. The brain detects relationships, sequences, regularities, and it applies its interpretive machinery to those patterns whether they are carried by acoustic energy or by its absence. Silence, structured correctly, speaks to the brain in the same language as sound. The temporal distortions that silence can produce are particularly interesting to sit with, because they connect to something most of us have noticed in everyday experience without necessarily having a framework to understand it. Time, in silence, behaves strangely. A minute of silence in a waiting room can feel far longer than a minute of engaging conversation. A quiet night can seem to stretch. A moment of acoustic emptiness before an anticipated sound, the pause before a piece of music begins, the silence before an answer arrives, can feel dilated, extended, weighted with a duration that the clock would not confirm. This is the temporal distortion effect of silence, and it appears to be genuine perceptual rather than merely retrospective. The brain, deprived of the acoustic events it normally uses to segment time and mark its passage, loses some of its anchor points. Without the stream of events to count and organize, the experience of duration becomes uncertain, and uncertainty, in perception, tends to expand. There is a related phenomenon sometimes called the one-is-more illusion, in which a single brief sound is perceived as longer in duration than a more complex sequence of sounds occupying the same objective time. The brain's estimate of duration is influenced by the density of events within an interval. More events make the interval feel shorter, fewer events make it feel longer, which is why a rich, eventful experience seems to pass quickly, while a sparse, uneventful one seems to stretch. All of these effects point toward a single underlying truth: we do not have a clock in our heads. We have something more like an event counter, a system that estimates duration from the density and structure of what happens within it, rather than from any independent measurement of time itself. And like all perceptual systems built on estimation rather than direct measurement, it is subject to systematic distortions when the conditions it evolved to handle are altered or removed. Silence alters them dramatically. It removes the events. It empties the counter. And in doing so, it does something that can feel, depending on your state of mind, either unsettling or deeply welcome. It stretches time. It makes a minute feel like more than a minute. It creates space where normally there is only motion. For those who seek out quiet, who practice meditation, or sit in still rooms by choice, or find themselves drawn to the long, unhurried hours of late night, this is perhaps the most useful fact in all of auditory science. Silence does not just feel longer. In a meaningful perceptual sense, it is longer. The brain lives more slowly in it. Time, in the absence of sound, has more room to breathe. And that room, it turns out, is not empty. It is where a great deal of the most important processing happens, the quiet consolidation of memory, the drift of attention inward, the unhurried reconstruction of what the brain has taken in during the noisier hours. Silence, as it was at the beginning of this journey, turns out to be the opposite of nothing. The illusions of silence and the illusions of sound produce identical results, which tells us, quietly but definitively, that the brain's relationship with sound was never really about sound at all. It was always about pattern, about structure, about the architecture of time itself. With that understanding settled, we can now step outward, away from the human ear and the human brain, and into the far broader acoustic world that surrounds us. Because we are, in the grand scale of things, relatively modest listeners. The range of frequencies detectable by the human ear, 20 Hz to 20,000, is a window, not a panorama. A useful window, shaped by millions of years of evolution to capture what mattered most in our particular ecological niche. But the acoustic world extends far beyond it in both directions, and the creatures that occupy those outer territories hear a reality that overlaps with ours only partially, a world of sound we can describe scientifically but never quite fully imagine. Below the lower edge of human hearing, below 20 Hz, lies infrasound. These are frequencies so low that the waves themselves become vast, stretching across meters or even kilometers of space. We don't hear infrasound in the conventional sense, but we can sometimes feel it, as a vague unease, a sense of pressure, an inexplicable feeling of being watched or of something being faintly wrong. Some researchers have proposed that infrasound may contribute to reported hauntings and other anomalous experiences in certain buildings, where structural resonance creates standing waves at frequencies below the threshold of hearing but within the range of physical sensation. Elephants are among the most accomplished users of infrasound in the animal kingdom. Their deep rumbling communications travel through both air and ground, detected not just by the ears but by sensitive receptors in the feet, which pick up the seismic component of the signal. A matriarch can send information about water sources or approaching danger across several kilometers of open savanna, and another herd can receive it, a conversation conducted at frequencies that pass entirely beneath human awareness, as though the elephants were speaking in a register the world keeps secret from us. Above the upper edge of human hearing, above 20,000 Hz, lies ultrasound. Here the waves are rapid and short, carrying fine detail and reflecting cleanly from small surfaces. It is a register that rewards precision, and the animals that work in it tend to be extraordinary navigators. Bats are the most celebrated. They produce ultrasonic calls, pulses of sound at frequencies typically ranging from around 20,000 to over 100,000 Hz, and listen for the echoes that return from objects in their environment. From those echoes, a bat can determine not just the presence of an obstacle or a prey item, but its distance, size, texture, and velocity. A hunting bat can detect a moth in total darkness, track its flight path, predict its trajectory, and intercept it, all through sound alone. The resolution of this system is remarkable enough that bats can discriminate between objects separated by a few millimeters, using ears and a brain that together weigh a fraction of a gram. Dolphins perform the same feat underwater, using biosonar to navigate murky water, to find fish hidden beneath the seafloor, and to communicate with members of their pod across considerable distances. Their clicks and whistles span a wide frequency range, and their ability to process returning echoes appears to exceed even that of bats in some respects, perceiving not just the outline of an object but something of its internal structure, which is why dolphins' sonar can, in certain conditions, detect air-filled cavities inside solid objects. A dolphin scanning a human swimmer with its sonar may receive information about the lungs and sinuses, an almost X-ray-like resolution achieved through nothing but sound. Dogs hear up to around 45,000 Hz, which is why they respond to ultrasonic whistles that produce no perceptible sound to human ears. Cats hear higher still, up to approximately 65,000 Hz, well positioned to detect the ultrasonic vocalizations of small rodents, which call to each other at frequencies their predators can track while most of the world cannot. Small mammals as a general category tend to hear at higher frequencies than large ones. The physics of this is partly mechanical. Smaller ears and smaller cochlea are better tuned to shorter, faster waves, and partly ecological, since small animals tend to communicate at frequencies that don't carry as far, limiting the range of eavesdroppers who might wish them harm. Sound is an animal's first warning system. Before you can see a predator, you can often hear it. Before you can smell a fire, you can sometimes hear the distant crackle. The soundscape of any natural environment carries a continuous stream of information about what is present, what is moving, what is approaching, and what has changed, and most animals are attending to that stream with a focus and discrimination that makes human listening look somewhat casual by comparison. The frog goes silent when a predator moves nearby. The bird changes its alarm call depending on whether the threat is aerial or terrestrial. The fish school responds to a pressure wave before any individual member has processed what caused it. Sound moves through the natural world as a shared medium of awareness, a nervous system distributed across an entire ecosystem, connecting creatures who have never met and may never see each other, through the common language of pressure and vibration. Houseflies, notably, are completely absent from this conversation. They possess no hearing organs of any kind, no structures capable of detecting sound waves. They navigate their world entirely through vision, touch, and chemical sensing, in a silence that is not chosen but simply the nature of their existence. It is a reminder that hearing, for all its ubiquity among vertebrates, is not a universal feature of animal life. It is a solution to a particular set of problems, detection, communication, orientation, that not every creature needs in the same form. Children, interestingly, hear differently from adults, not in terms of what they understand, but in terms of what their ears can physically detect. Human infants can hear above 20,000 Hz. Young children typically retain sensitivity into the upper ranges that adults have already begun to lose. The gradual narrowing of the high-frequency range is one of the earliest and most consistent features of aging in the auditory system, beginning, almost imperceptibly, in the late teenage years and continuing slowly throughout life. The frequencies go first at the top, the thin bright tones fading from perception while the richer mid-range persists. There are high-frequency tones, around 17,000 to 18,000 Hz, that most adults over 30 cannot hear at all, but that teenagers can detect with ease. This frequency difference has been used, at various points and with varying degrees of controversy, as the basis for devices designed to disperse teenagers from public spaces, and for ringtones designed to be audible to students but not to teachers. The physics is simply the biology of aging, exploited practically. What we hear, then, is not a fixed or universal thing. It shifts through our lifetime. It varies between species. It exists within a much larger acoustic universe that extends outward in both directions from the narrow band our ears were built to occupy. And within that larger universe, sound is not merely a signal. It is a force. This is perhaps the most counterintuitive aspect of acoustics, the idea that sound, which we experience as something so insubstantial, something that seems barely to exist physically at all, can exert real mechanical force on real physical objects. But it can, and it does, and the demonstration of this principle is one of the stranger spectacles in experimental physics. Acoustic levitation is real. It is not a metaphor, not a science fiction premise, not a theoretical possibility awaiting practical realization. It is a reproducible laboratory technique used in research facilities around the world. By generating precisely tuned standing waves, sound waves reflected back on themselves to create stable patterns of constructive and destructive interference, it is possible to produce nodes, points where the pressure variations cancel out and the net acoustic force is directed inward from all sides. A small object placed at such a note experiences balanced radiation pressure from the surrounding sound field and, if the conditions are right, will float there, suspended in air by nothing but carefully arranged sound. Water droplets, small beads, tiny biological samples, lightweight granules, all have been levitated this way. Researchers use acoustic levitation to handle samples that cannot be allowed to touch any surface, to study the behavior of fluids in weight-like conditions, and to manipulate delicate materials without contamination. The frequencies used are typically ultrasonic, above the range of human hearing, which means that the experiments often happen in apparent silence, the levitating force invisible and inaudible, the suspended object drifting gently in midair with no visible means of support. It is a demonstration that cuts to the heart of something easy to forget. Sound is energy. It is not just the experience of energy, not just a representation of energy reaching your ears. It is energy moving through a medium, exerting force, doing work. The same phenomenon that allows you to hear a whisper is, at sufficient intensity and the right frequency, capable of holding physical matter in place against the pull of gravity. The universe, it turns out, is not merely full of sounds. In a very real sense, it is shaped by them. Sound can put out a fire. This is not a gradual effect, not a slow smothering. It is something that happens quickly and directly, and watching it occur for the first time tends to produce a particular kind of cognitive dissonance, the feeling of seeing two things happen together that your intuition insists should have nothing to do with each other. A flame, burning steadily. A sound wave directed toward it. And then the flame bends, thins, and goes out. The mechanism is straightforward once you understand it, but it takes a moment to absorb. Fire requires a continuous supply of oxygen at its base, where the fuel and the heat meet. A sound wave moving through air is a pattern of compression and rarefaction, alternating zones of higher and lower pressure moving outward from the source. When that wave passes through the region where a flame is burning, it disturbs the boundary layer of air surrounding the combustion zone, disrupting the steady flow of oxygen to the base of the flame. At sufficient intensity and the right frequency, typically low frequencies, in the range of 30 to 60 Hz, the disruption is enough to separate the flame from its fuel supply. The fire doesn't so much get extinguished as get disconnected. Researchers have built prototype firefighting devices based on this principle, handheld acoustic extinguishers that direct low-frequency sound at small fires, putting them out without water, without chemicals, without foam. They are not yet in common use, but the principle is established and functional, and the image of a burning object falling silent in response to sound carries a kind of quiet poetry. Fire and sound, two of the oldest presences in human experience, arranged in opposition. At the other end of the intensity scale, sound can destroy. The phenomenon of a singer shattering a wine glass with their voice is real, though it requires the right conditions. Most importantly, that the voice produce a note at or very near the resonant frequency of the glass. Every physical object has natural resonant frequencies, determined by its shape, size, and material properties. When energy is introduced at that frequency, the object vibrates more and more vigorously, because each new wave of energy arrives just as the object's own oscillation reaches a favorable phase, reinforcing rather than damping the motion. This is the principle of resonance, and in the right conditions it can build to the point where the object's own vibration exceeds its structural tolerance. A wine glass, driven to resonance by a sustained tone at precisely the right frequency, will flex with each cycle of vibration. If the amplitude is large enough, if the singer maintains the note with sufficient volume, the flexion becomes too great for the glass to absorb, and it shatters. The sound didn't hit the glass like a physical blow. It invited the glass to vibrate itself apart, one cycle at a time. The same principle underlies one of the more dramatic acoustic phenomena in everyday life, the crack of a whip. That sharp, explosive sound is not the whip striking anything. It is a miniature sonic boom, produced when the tip of the whip moves faster than the speed of sound. As the wave of motion travels down the length of the whip, it accelerates, the same energy concentrated into a progressively smaller and lighter section of cord, until the very tip exceeds Mach 1, the speed of sound, and produces a small shockwave. The crack is the sound of that shockwave, the same physical event that produces the roar of a supersonic aircraft, scaled down to the size of a wrist flick. Mach 1, the speed of sound, is the threshold at which an object's motion begins to outpace its own acoustic signature. Below that speed, the pressure waves produced by a moving object spread ahead of it, giving the surrounding medium a kind of advance warning. Above it, the object arrives before the sound of its own passage, compressing those pressure waves into a shock wave that trails behind it. Mach numbers, named for the Austrian physicist Ernst Mach, simply express speed as a multiple of the local speed of sound, which, as we established earlier, varies with temperature and medium. Mach 1 in warm air at sea level is roughly 1,235 kilometers per hour. In cold air at altitude, it is somewhat lower. Below the threshold of hearing, sound continues to be felt even when it cannot be heard. Infrasound, frequencies below 20 Hz, doesn't register in the cochlea the way audible sound does, but it interacts with the body in other ways. At sufficient intensity, low-frequency sound can induce vibration in body cavities, create sensations of pressure or discomfort, and produce physiological responses that seem to arise from no identifiable source. The experience tends to be vague and disorienting, unease without a clear cause, a sense of the atmosphere being somehow wrong. Filmmakers have known about this for decades, and some have used it deliberately. Certain horror and thriller films have incorporated infrasound into their soundtracks, using frequencies in the range of 18 to 19 Hz to produce in the audience a subtle but genuine physiological response, a low, unspecific dread that layers beneath the audible content of the film and reinforces the emotional atmosphere without the viewer ever identifying it consciously. The feeling seems to come from the film's imagery or story, but some of it is coming from the acoustic environment, from sound the audience cannot hear but the body quietly registers. Whether this technique is as widespread or as effective as some accounts suggest remains a matter of some debate. But the underlying physiology is real. The body responds to infrasound. And a storyteller who understands this has access to an instrument that operates below the threshold of critical awareness, reaching something more primitive than conscious attention. Sound, across its full range, is a physical force that does not confine itself to the experience of hearing. It bends flames. It shatters glass. It breaks the sound barrier at the tip of a whip. It vibrates the body at frequencies below hearing. And at the upper extremes of natural intensity, it achieves things that are genuinely difficult to hold in the mind. In August of 1883, the volcanic island of Krakatoa, in the Sunda Strait between Java and Sumatra, underwent one of the most catastrophic eruptions in recorded human history. The final, largest explosion, which occurred in the early morning hours and was heard from a distance that has never been matched by any other recorded sound, was not merely loud. It was the loudest sound human civilization has ever documented. The eruption was heard clearly in Australia, more than 3,500 kilometers away. It was heard in the island of Rodriguez, near Mauritius, roughly 4,800 kilometers to the southwest. Barometric pressure gauges around the world registered the atmospheric shock wave as it traveled around the Earth, not once, but multiple times, the wave circumnavigating the globe several times over the following days before finally dissipating. The explosion threw material into the atmosphere that affected global temperatures for years, and generated a tsunami that killed tens of thousands of people across the region. The estimated sound level at the source has been calculated at around 172 decibels, measured at 160 kilometers from the eruption. At the source itself, the figure would have been vastly higher. By any measure, it stands as a singular event in the acoustic history of the planet. To understand why these numbers matter, it helps to understand the decibel scale itself, because it is not a linear scale. Every increase of 10 decibels represents not 10 units more of acoustic power, but 10 times more. This is a logarithmic relationship, built to reflect the extraordinary range of intensities the human ear can detect, from the faintest perceptible whisper to sounds that cause immediate physical damage. A sound at 30 decibels is 10 times more powerful than a sound at 20 decibels. A sound at 40 decibels is 10 times more powerful than that, 100 times more powerful than the 20 decibel sound. By the time you reach 100 decibels, you are dealing with 10 billion times the acoustic power of the threshold of hearing. The scale compresses an almost incomprehensible range of intensities into numbers that remain manageable only because they are logarithmic. This exponential growth has a physical limit. At 194 decibels, a sound wave in air reaches a boundary condition. At this level, the rarefaction portion of the wave, the low-pressure phase, would need to drop below 0 pascals of absolute pressure in order for the wave to continue propagating in the conventional sense. But 0 pascals is a perfect vacuum, and air cannot sustain negative absolute pressure. The wave cannot go lower than nothing. What happens instead, at and above this threshold, is that the nature of the wave itself changes. It transitions from a conventional sinusoidal pressure wave to a shock wave, a discontinuous front, a wall of pressure that moves differently and interacts with the medium differently. The 194 decibel figure represents the theoretical maximum amplitude of a sound wave that can propagate through air in the conventional sense. Beyond it, you are no longer dealing with sound is usually defined. This is, in the most literal sense, the loudest sound air can carry. Not the loudest sound that has ever occurred, the interior of a star, or the shock wave of a nuclear detonation, or the collapse of a neutron star involve energy releases that dwarf anything achievable in air at ordinary pressures. But in the specific medium we live and breathe and hear within, 194 decibels is where the physics of sound reaches the edge of what it can sustain. The universe, for all its immensity, operates within rules. Sound, for all its power, its ability to travel through mountains, to suspend matter in midair, to extinguish fire, to shatter glass, to carry information across ocean basins in geological time, is bounded. It has a ceiling. It has limits that the physics of the medium enforce absolutely. And within those limits, contained within the range between the faintest whisper and the theoretical maximum of what air can carry, lies the entire acoustic world that all of us, every creature that has ever heard, every civilization that has ever listened, have lived within. At the absolute boundary of what air can sustain as sound, at 194 decibels, something unusual happens to the wave itself. The rarefaction phase, the low-pressure trough that follows each compression, would need to pull the air below zero absolute pressure to complete its cycle normally. Since that is physically impossible, the wave doesn't complete that cycle in the conventional way. Instead, it collapses into something closer to a shock wave, and in doing so, it briefly creates pockets of near vacuum, regions where the air molecules have been so violently displaced that almost nothing remains in that space for a fraction of an instant. The sound, at its absolute limit, momentarily unmakes the medium it needs to travel through. It is a fitting image to carry forward as the story of sound begins to turn toward quieter territory. The most extreme expression of acoustic energy creates, at its peak, a tiny window of silence. Force taken to its limit produces, briefly, its own opposite. From here, the story softens. The ocean in a shell is not the ocean. Most of us encountered this as children, the instruction to hold a shell to the ear and listen for the sea. And there is something genuinely there, a soft, rushing presence that does carry a certain resemblance to the sound of distant surf. But what you are actually hearing has nothing to do with where the shell came from. It is the sound of the air trapped inside the shell's cavity resonating in response to the ambient sound energy already present in the room around you. Every enclosed space has resonant frequencies at which it vibrates sympathetically, reinforcing certain wavelengths and suppressing others. A shell, with its smooth curved interior, is particularly effective at this. The ambient noise of the environment, the low hiss of air movement, the distant hum of machinery, the quiet acoustic texture of any inhabited space, contains energy across a wide range of frequencies. The shell selects from that energy, amplifying the frequencies that match its resonant profile and returning them to your ear as a smooth, continuous tone. The result sounds vaguely oceanic because broadband noise shaped by resonance often does. The same principle underlies the sound of wind in trees, or water in pipes, or the murmur of a crowd heard from a distance. Hold the same shell in an anechoic chamber, where there is almost no ambient sound energy to drive the resonance, and the ocean disappears. The shell is silent. It was always borrowing the sound from you. The relationship between sound and living things extends in directions that are still being mapped by researchers. cows exposed to slow, calm music, pieces with tempos in the range of 100 beats per minute or below, have been shown in several studies to produce modestly higher volumes of milk than cows in quieter or more sonically stressful environments. The effect is not enormous, but it is measurable and reproducible enough to have been taken seriously by agricultural researchers, and some farms have implemented music programs as a result. The proposed mechanism involves stress reduction, lower cortisol levels and calmer acoustic environments, leading to more relaxed animals and more efficient physiological function. Sound, arriving at the right frequency and pace, shifts the body's state. This is true for humans and, it appears, for other mammals as well. The strangeness of hearing your own recorded voice is a small but genuinely interesting acoustic phenomenon, and almost universally experienced. When you speak, you hear yourself through two pathways simultaneously. Sound travels through the air to your outer ear in the normal way, but it also travels through the bones and tissues of your skull directly to the cochlea, bypassing the outer and middle ear entirely. This bone conduction pathway transmits the lower frequencies of your voice somewhat more efficiently than air conduction does, which means that the voice you hear in your own head contains more bass than the voice a microphone captures. The recording, picking up only the air-conducted signal, sounds thinner, higher, and less resonant than what you are used to. Neither version is wrong. They are simply two different acoustic measurements of the same source. Bone conduction is also the principle behind a category of hearing devices designed for people with certain kinds of hearing loss, devices that transmit sound directly through the bones of the skull to the cochlea, bypassing a damaged or absent outer or middle ear entirely. The cochlea receives the signal and processes it normally, because the problem was never in the inner ear. The ear, in this sense, is not strictly necessary for hearing. The cochlea can be reached by other routes. This points towards something more general about how size and resonance interact. Large objects resonate most efficiently at low frequencies. Their physical dimensions accommodate the long wavelengths of bass sounds more naturally, which is why large instruments, large rooms, and large speakers tend toward richer, deeper tones. Small objects resonate at high frequencies, their compact dimensions suited to shorter, faster waves. This is why a piccolo is small and a double bass is large, why a child's voice is higher than an adult's, why the resonant hum of a large cathedral sits far below the ring of a small crystal bell. The universe scales its acoustic character with physical size, and once you notice this relationship, you hear it everywhere. And now the story arrives where it perhaps always intended to, back at silence. But a different kind of silence than the one we began with. Not the silence of an anechoic chamber, or the silence of outer space, or even the silence that stretches time. A more philosophical silence. The silence that asks what it means to perceive the absence of something. We hear silence. This seems obvious enough. Of course we notice when sound stops, when a room goes quiet, when the music ends. But the philosophical weight of that simple observation is more significant than it first appears. Hearing silence is not the same as simply failing to hear anything. When a sound stops, there is a distinct perceptual event, something is heard as having ended, and the absence that follows is registered as its own kind of presence. The silence after a piece of music is not the same as the silence before it began. It has a different character, a different weight, a different meaning. It carries the memory of what it follows. Philosophers of perception have argued about this with considerable care. When we hear silence, what exactly are we perceiving? We are not perceiving a sound. Silence is, by definition, not a sound. We are perceiving an absence. And yet the experience is genuine, not merely inferential. We don't conclude that silence has arrived the way we might conclude from indirect evidence that something has happened. We hear it, directly and immediately, as something present. Some philosophers have suggested that hearing silence is a case of perceiving an absence, a genuine perceptual object that happens to be defined by the lack of something rather than by its presence. The silence after a loud sound is not just the absence of that sound, it is that specific absence, in that specific context, carrying that specific quality. It is different from other silences, and we perceive those differences. This is unusual. Most of our perceptual categories are built around presences, things that are there, things we can point to and describe. Absence is typically something we infer from the failure of a presence to appear. But auditory silence seems to be something we genuinely perceive rather than infer, something that registers in the brain's processing as an event in its own right, not a gap between events but an event made of gap. The neuroscience we visited earlier supports this. The brain processes silence actively. It generates predictions about what should arrive and tracks their non-arrival. It segments silence into durations and attends to its structure. What a brain does with silence and what it does with sound are, at the neural level, not as different as they might seem. And yet there is something else, a layer underneath even this, that makes silence philosophically unique. Silence doesn't cause anything in the way that sounds cause things. A loud noise causes a startle response. A spoken word causes comprehension. A piece of music causes an emotional reaction. These are causal chains, running from acoustic event to physiological and psychological effect. But the silence between a heartbeat and the next one, the quiet between movements of a symphony, the pause after someone says something important and before they say anything more, these silences do not push on us the way sounds do. They have no acoustic energy to deliver. They exert no pressure. And yet they matter. Often they matter enormously. The pause in a conversation can communicate more than the words surrounding it. The silence at the end of a piece of music is often felt as the most important moment of the whole, the place where everything that was said finally settles, where the resonance of what came before is allowed to complete itself in the listener. A held silence between two people can be tender or tense, comfortable or unbearable. None of this is caused by the silence in any direct physical sense. It is meaning read into the absence, carried there by everything the silence surrounds. We are, it seems, uniquely prepared to find meaning in what isn't there. To hear what isn't sounding. To feel the weight of the pause, the significance of the space, the presence of the absence. Which brings everything, at last, to this moment. Whatever sounds surround you now, or don't, your auditory system is attending to them. Your brain is building its model of the acoustic world, monitoring the silence, tracking the patterns, waiting for the next event, constructing from pressure waves and electrical signals and learned predictions, the seamless experience of a world that sounds a certain way. The science of sound begins with vibration and ends, somehow, here, in the quiet, in the in-between, in the extraordinary fact that a pattern of pressure moving through air can arrive at a nervous system and become, by some process still not fully understood, an experience. That the mechanical can become the meaningful. That vibration can become feeling. And that silence, the absence of all of it, can be just as full.